what are the ingredients going in that? So I'm trying to teach you the semiconductor properties, the band gap, and so forth. But then as we add dopants and charge, how are the free carriers going to move around? So that's why I tried to introduce you a little bit into some process understanding, so you can have a little deeper understanding of oxide formation and so forth. Some of the key ingredients to making these. So you have a little better understanding, deeper appreciation. Okay. This is higher order. Hopefully you get this in sort of 2100. This is your DRAM capacitors. You know, when you extend the memory, that's what it looks like. This is a whole circuit and so forth. But anyway, the heart of it starts off material properties, crystallography. Okay, so we're interested in these particular semiconductor materials that condense down into a crystal. And so you can think of so I was trying to relate things like the materials can start off, they can have an amorphous or polycrystalline or crystalline. Obviously, for a high-end transistor, we're going to want it to all be crystalline. So, you don't have to necessarily go back to redoing freshman chemistry, bonding, and all that, but understand that that's what we're starting with is the valence electrons. You know, the different orbitals and so forth, and the valence electrons. And that builds a framework for how this is going to bond. And we're interested, mostly in things like silicon as our go-to material, where we've got things going on, 2s, 2p, and so forth states. And silicon's not there, but the valence electrons. So here we're interested, and so understanding that there's this wave-particle duality. We have sort of the wave, electron going around, discrete, but it's got a wave cloud associated with it. And so from a manipulation of that, and we're pretty much interested in, boy, I'm going to get a real workout here. What we're really interested in is the column 4 or the 3 and the 5s. I'm kind of dismissing for this class the wacko ones, the 2-6 ones, and so forth. They're very small subset of the demographic of semiconductor technology. They are out there. They have their niche applications and so forth, infrared detectors and stuff like that. But generally speaking, it's the column 4 and 3 box. Okay. So as we go, so the ionic bonds are not really in the class of semiconductors. And it's partly because, you have a lump of sodium chloride or so, that's classic ionic. They just helter-skelter combine in any direction. Okay, the covalent now starts to have a greater directionality to it. And the particular ones we're interested in, and I guess the directionality comes up later, but recognize there's a preferred interatomic radius, distance, and that in reality, as we add kT temperature to the system, the preferred distance is oscillating between there. You can think of it as the ball and spring here mode, and so it's oscillating between that. So that's the quiescent point or so forth. But as you add kT, as you add thermal energy, it gets excited around that. Kill this thing. Now it's in the way. So this is where I was trying to point out crystals is the building blocks, polycrystalline, and you know, so things are. If you had if you liquefied this, and that's what happened here, sort of an arc welding beam, electron beam came through here, and this actually turns to a puddle of, what is it, iron, I assume? Something like iron. Oh, no, niobium, hafnium, tungsten plates. Okay, so some metal hybrid. And so this got melted, and it spontaneously nucleated. And what is that? Some atom will spontaneously join up with another atom and start to become the building block of a crystal. And so at some point, somewhere, just Mother Nature, the randomness of nature, there in the center of this sort of whitish crystal, probably two atoms decided to get together and lock up. And then another one came in and started to build out the crystal in the way it's supposed to. But somewhere over here in this brown flake, in another neighborhood, in another county, some other couple atoms got together and they started to pull in other atoms and nucleate. And so their orientations relative to each other are completely random. So within each flake, within each grain, it's completely crystalline. So now that I've kind of talked to you a little bit about electron transport, you can see that an electron going through the center of that grain, that flake, is going to behave very well because the crystal is very periodic and everything's well behaved. But once I get to the edge of that crystal, I have opportunity for scattering. So that's going to lower my mobility and things like that. So now hopefully it makes a little more sense. And here's the grain boundaries. Now maybe it makes a little more sense when I show this thin film this liquid crystal display with the thin film transistors. TFT is shorthand for thin film transistor. And I was pointing out that driving that pixel is a silicon transistor. And so that silicon, which wants to be crystalline, was deposited onto an amorphous glass plate. So the silicon got confused. It went down cold. It went down on the amorphous glass. It didn't know how to crystallize. And so it went down, and it was also amorphous because its substrate was amorphous. And so therefore, my mobility of that material was very low because it's just so random, so much scattering opportunity. And maybe I came in judiciously with a high power laser, and I sort of, without killing the glass or anything, without hurting other parts, I just delivered a little bit of heat pulse and sort of caused that locality of silicon to melt. And then I give it enough time, it slowly condenses and recrystallizes like that arc weld, and maybe it'll manifest as more of a polycrystalline material. So I just gave it temperature and time. Those are two key ingredients. And so now I got a polycrystalline, so now I got a higher mobility. And in fact, the key will be, I've not This is where I'm leading you to. This is why I was trying to introduce you to the topology of a transistor from day one. This is one of the distinguished people at Intel had this. This is public release slides from Intel from a number of years ago. And so they break up this transistor, and we're going to be getting into this when we get into transistors. But this is basically vocalizing what is the current, the drain saturation current, as a function of the different biases. What I wanted to call your attention to, the things we've already covered: mobility and capacitance of this oxide, this thin oxide. And so you can see that I actually make this transistor better when I increase the Cox, because that's in the numerator. So the Cox is basically the capacitance of the gate, which is, it doesn't show up very well because they used white font on a bright background, but it's the epsilon naught and the epsilon s I talked about just a couple of lectures ago over Tox, the thickness of the oxide. So you can see some of the driving force that one of the things the Intels of the world are doing is either raising the permittivity of this dielectric, or they're making the dielectric thinner and thinner and thinner. The other thing I need to call your attention to is the mobility. And that's what we're talking, when I'm talking about the thin film transistors in the active matrix. The mobility is also in the numerator, so it's directly correlated to the performance of that transistor. So I increase the mobility, I choose a better material, or I have a higher quality material, and I realize the true mobility in its full glory, whatever the speed limit is of that particular material. I'm going to get a better mousetrap. I'm going to get a better transistor, a better performer. So that's the driving force of everything. Okay. So that's one of the things we're shrinking. So it's a structure property relationship, essentially, where I have better crystallinity, and that leads to better mobility because I have less scattering with the amorphous nature. If I have larger grain, if the polycrystalline is even larger grains, then I have even less scattering. If I got a lot of small grains, there's a direct relationship, structure versus property. Okay. So then I tried to point out, so again, this, this preferred atomic spacing. That's all that crystallography, Miller's indices. I probably will not emphasize much about Miller's indices, crystallography. Those kind of things are better on homework questions and so forth. Calculate the 111. That's not what this is about. This is the big picture. So I'm more interested in things like this. So the covalent bonds lead to directionality. And so the materials we're interested in happen to do this sp3 hybridization, where the s orbitals are always spherical, p orbitals are always these dumbbell shapes. And since we have in the p orbitals, we got six valence electrons, right? We got 2 in the y, 2 in the x, 2 in the y, 2 in the z. So I got 3 dumbbell shapes sticking in the 3 directions on the 3 axes. But they get together and they form this lobe. And so then I end up having 4 of these lobes that are pointed very clearly in a particular direction. And that's an electron cloud. And if I haven't made that very, very clear, those electron clouds don't like each other. They repel each other. So they end up going very directionally in these, so it's filling the 2 pi steradians, all space around that particular atom. And these things are as far apart from each other. They do not like each other. They're as far apart as from each other as they can. So every one of these angles is 109.5 from each other. That's the closest you can get. If that was 109.0, then it means the other one is 110, right? And so if it comes closer on one side, pushes away from one side, it comes closer to the other guy, the guy on the other side. So there's this push-pull. Now, probably the whole thing is oscillating a little bit, with a KT, a little bit of energy and so forth. So there's probably a little bit of a stretch and so forth in there. But that's basically it. So that becomes our Tetris building block. right? This is my Egyptian block of stone, and I'm going to build my pyramid with it, okay? And so then I build it, and I build something like this. I build like silicon, where it's really the two FCCs interposed with each other. And so this is your classic diamond, and also silicon, same family. But what I need to have you recognize is that all of these atoms now are in a predictable location relative to each other, right? Because of the directionality of the bonds and everything, I can predict that there's an atom here. I can then predict that there's another atom over here, another A away, and it's going to be just A. So now I can predict where everything is. So you know that what's coming in the next story a little bit later is I get the derivation of band gap. And therefore, the carriers going through that band gap are experiencing the same periodicity in this direction, but they're experiencing a different periodicity if they're going sideways or diagonally, right? So now just think of you, now look at this crystal with a fresh set of eyes, and I'm now an electron going through this crystal. The periodicity is now going to be the imposing boundary conditions of the carriers going through that. And that's going to set the band structure and the K and so forth that it's going to see. So with the crystallography, we can do something. We can manipulate the crystallography where the wafers are usually 100 plane, and then to make sure that in the factory we don't get them mixed up with each other, they do things like this where they do this tagging, this marking, so that everybody knows without having to go to do an electrical measurement exactly what it is before you even take it out of the box. And we can manipulate it. We can do things like this, like the MEMS actuator in your airbag deployment system. So it uses things like this, where it's using certain crystallographic planes to etch certain, and it etches a capacitive diaphragm that basically leads to this accelerometer and so forth. So we can manipulate silicon now that it's highly crystallographic. We can etch along certain planes and things like that. And so we can do all that. Or we can make waveguides. Like one of the things that's probably coming down the pipeline is things like this, waveguides perhaps, that we're going to be moving a lot of those nasty interconnects you saw at the beginning. Right? This is getting so ugly in an integrated circuit that probably there's going to be more and more photonics being added to this chip, replacing some of these nasty wires. So we may end up with a hybrid. In my prediction, the transistors will always be semiconductor, be electrical. Let me say electrical. And the interconnects may, though, go to a hybrid optical. And so you can do all kinds of interesting things where I can machine this, and therefore I can precisely put an optical fiber right down into this recess where I put a round fiber right in there, and I know exactly where it is. I know right exactly where the light beam is going to be coming out because I've micro machined. This is the other beauty of silicon that's not well talked about, is it can be machined so easily because it's a beautiful crystallography. Okay, so here's things like I was giving foreshadowing when we get into laser diodes. I can cleave it along the atomic planes just like I'm a diamond cutter, and that cleave is actually, if it's done properly, is one atomic, is actually zero atomic roughness. It's one atomic plane where I've cleaved this thing. And so then I build a mirror out of that and turn that into a laser diode. We'll talk more about that when we get into diode applications. And yeah, these are, examples. This can be done. This is what I did in my own handiwork when I was a PhD student. This is a waveguide, and I cleaved it, and it's kind of a copy of a copy of a copy, so it looks very black, like a black smudge. But believe me, that was really smooth. And there's an artifact of the camera, these kind of extra dots up there, but this shows you the light beams going through that waveguide. So I could distribute a clock signal around my integrated circuit, perhaps, by sending light beams through the micro machine silicon. So so obviously materials become very key. What's the crystallinity, what's its orientation, that's all going to matter. So obviously we have to know how to inspect it. So just understanding some of the ways I might go in and probe this is way more than I can possibly cover in this class. But one classic way, real simple way, is just do an electron diffraction. X-ray diffraction. So I just using the crystal as a diffraction grating, bouncing beams off of that. And so, I'm just kind of rekindling your diffraction theory, diffraction through a slit, and you get the Fourier transform of that. And so the Fourier transform is displayed it's projected onto the screen. And so this is the Fraunhofer diffraction. You get a sine x over x, basically. That's what that is. And so you get beams like this, diffraction beams. And I was kind of pointing out as an aside, because I come from an optics background and so forth, I can even do real-time image processing on this and so forth. But with the diffraction theory, I can quantify, I can query, is it amorphous silicon? Is it polycrystalline silicon? Is it single crystal silicon? And I can maybe even determine the orientation by the diffraction pattern, which I need to know because some of those process dependencies like diffusion, ion implantation, that I kind of expose you to, that's going to matter depending upon which orientation I am relative to the crystal, because it may be denser in certain directions and less dense in others. So the diffusion may go faster in certain directions than others. So I need to know the orientation of my wafer. And so here's the crystal diffraction from that. And so you get different peaks. By measuring the peaks, you can see where it is. Again, this is sort of that structural property. You can see the diffraction pattern change as I'm going from completely amorphous to crystalline and in between. So defects are usually bad, with the exception of the substitutional one, right? Because that's the one where we're probably going to be trying to introduce an electrically active dopant. Right? So we can usually like that if it's impurity of our choosing. We don't want an impurity not of our choosing, of a contamination. And sometimes the impurity to get to it substitutionally, sometimes it might be caught in an intermediary, kind of like musical chairs, and you get one person left out momentarily. So this guy isn't quite found his happy home. He's not sitting in his chair. He's in the in-between spot. But here's a vacancy, for instance. So that guy may be moving towards that vacancy and eventually pop into place. So maybe those two will combine, an interstitial and a vacancy, and create a substitutional. This guy was knocked out of place. He could have been knocked out of place by that ion implantation. Remember how violent that was. And I tried to point out to you things like your flash memory and so forth, of being able to have little nanocrystals. You're loading up charge into that, so you can see the usage of polycrystalline material. There's another application. Yeah, so here's the. Now we can have dislocations. Now this is a line dislocation. This is a line defect. So we're missing you know, this one row of atoms just stops, and we're missing a particular row. So therefore, this is a defect, a line defect into the. So therefore, every one of those atoms recognized has a dangling bond, so it's unhappy, right? It's a dangling bond, and therefore there's some charge associated with that. That could lead to, now that you started to flash forward a little bit into, that could be creating a trap level, an ET, in the band diagram, right? So a defect could manifest, you don't know, depends on the type of defect, but it can create a trap. And we don't usually like these things in our forbidden band gap. And now I got a lot of these because every one of those atoms is producing one into the board, the whole line. So the point defects only introduce one, whereas the dislocation produces everything along its spline. Now, you know, not all dislocations are necessarily the same. Screw dislocations are pretty hazardous to electrical devices. The misfit dislocations that I'm going to talk about next aren't always as bad. And so, you know, as we go through and we put one band gap on top of another band gap, we have to worry about lattice constant mismatch. And so if I take an easy one, I put gallium arsenide and aluminum arsenide on top of each other. They're right on top of each other vertically with the same lattice constant. So that's an easy one. In fact, that was the first one developed in the late 60s, early 70s. It took a little bit longer for us mastery and maturity to be able to get into this indium phosphide one, to be able to do indium and gallium arsenide. That started to develop in the later 70s and into the 80s. And so forth. So, but it's trying to put an InGas that's probably pretty tightly in registry with the indium phosphide. And if you don't put it in registry, you can risk having a misfit dislocation, right? And that's where your lattice constants are different, and there will be a point at which it constrains, pushes, and there's a deformation. And so I can stretch my the skin across my drum pretty tightly because it's pretty thin. But if I make that skin thicker and thicker and thicker, eventually it's just going to crack. And that's what, you know, I end up with these misfit dislocations. Now, misfits aren't as, don't get confused, because misfits aren't always dramatically hazardous to our device. I would prefer them not to be there if I could, but they're not as detrimental as others. So I tried to put in a box to focus your attention. I don't need you to know all this, but basically this is kind of the definition of critical thickness. It's just when it becomes, as you pile more and more on, when does it become, as critical thickness is when it becomes energetically favorable to produce the misfit dislocation. So that is the critical thickness. That's the point at which it pops. And so you can see this is experimentally determined critical thicknesses as a function of the alloy composition. And as I mentioned, actually, in my old PhD studies, I was looking at that, again, one of those diagnostic techniques. I was looking at high energy electron diffraction bouncing off of the crystal, and I could see, infer what the crystal looked like from its Fourier transform. And so, I don't think I ever mentioned that, but the reason these ended up into bars, into lines, is when this bounces off the crystal and goes to my diffraction grating, which in this case is just a window coated with phosphorus, so when the electron beam hits it, it glows with those lines. And that over here, I'm in reciprocal space. So that means x becomes 1 over x, 1 over y, 1 over z. right? And over here, I'm in real space, x, y, z. So I'm in reciprocal space. This is the Fourier transform. So everything's inverted. And the reason this goes to a line is because if my surface is as smooth as it's supposed to be, z goes to a 0 atomic thickness. And I get a divide by infinity. I mean, divide by 0, so I get infinity. And that means it stretches into a bar. And that tells me that I got an atomically flat surface. And when I lose that atomically flat surface, I'm back to a three-dimensional. In fact, what ends up happening there is I would have a little quantum dot box. My beam would be going through there. And it's interrogating this three-dimensionally. And that's when this goes back, condenses back into a bunch of discrete dots. And when, so no longer I have a divide by 0. And so you can see at the so really it takes 2 layers to really complete. When you do gallium arsenide, realize you have to put an atomic layer of gallium and an atomic layer of arsenic to actually complete one monolayer, right? Because it's the combination that really makes. So I can actually see every evolution of this. And yeah, that's my old data. Well, the bottom, and that's the patterns. And yeah, this is my old data. So I can actually see very dramatically where that misfit is formed. Okay, so now we can see what's inside. We know some of the crystallographic constraints on the system. Come full circle, and so that puts a boundary condition on how I can, how much germanium I can put in here before the whole thing starts to crack. Right? So there might be a limitation on that. And so those are the misfits. Okay. So now we just need to know how are we going to make all this? Well, we got the Czochralski, we pull out a boule. We have the molten silicon, so we have all these techniques. This is probably the classic one, the go-to one. A lot of former Eastern European, Poland and so forth, some still to this day tend to be some of the best places for bulk crystal growth. So that's the substrate of developing new techniques. So here's the melt, the crystal, another picture of it, and that's what it looks like. And it's crazy. I think the movie might have shown, this little tiny seed crystal is used as the starting point. And they pull out these boules that are like, 4 feet tall and, 300 millimeters around or so. And you can imagine how heavy they are. You're just wondering why it doesn't fall over. It still boggles my mind. And so then you slice and dice and polish, determine the orientation and everything, and you get a happy camper and with his bunny suit in the clean room, hopefully making integrated circuits. Okay. So here's another way, float zone. You just sort of pour a jello mold, and it condenses and becomes polycrystalline, like the other thing. So we just pour into sort of a mold the material. But then we go back and comb it, and kind of like comb out the tangles, if you will. And so you do this enough times, back and forth, eventually you comb it to be somewhat fairly single crystal. The beauty of that is it's not really an intimate contact with a crucible, and anything, this is molten, so anything it's in contact with will suck up contamination. So you see how this is more of a non-contact method. You only contaminate at the very beginning when you poured it into the mold. So this is the phase diagram, which is a little bit beyond this, but you heat it up to liquid, to this above the liquidus, cool it down, and it actually ties over, comes over to this tie line, and it condenses out as stoichiometric gallium arsenide. It was a huge discovery in the early 70s when they could realize that they didn't have to get the gallium and the arsenic ratio exactly 1-to-1 to 9 significant digits, Mother Nature, through the phase diagram, means that it only allows it to condense in 1-to-1 ratio. So Mother Nature gave us a good one there. And you got these other techniques, Richmond, so you got all these things. So obviously now I have a substrate, and I want to make a semiconductor, and I want to modulate its conductivity for all these wonderful devices I want to make. And so the only way I can modulate the conductivity is by modifying the substrate, by introducing those impurities. And so this one is the diffusion that I have the take-home problem. So I'm just introducing through a gas. There's another technique that's less hostile. I think before the video started, I was trying to scare everyone with things like toxic phosphine gas. You can also do spin-on glass, where it's a liquid glass that condenses into a solid glass impregnated with the dopant of your choice. That's much more user-friendly. That's something university, even undergraduate researchers could work with easily. This is, you need an expensive machine to do the ion implantation. You basically have a mini railgun, and you're just shooting impurities below the surface. So you can see how the peak is below the surface depending upon your ion energy. So it just takes whatever source gas you want. Somewhere, ion source, I don't know. You just pull in whatever gas you want, and you ionize it, and then you accelerate it through a voltage. And so you make it +1 or -1 or so forth, and then you accelerate it through 1,000 volts, and you're getting 1,000 electron volt energy, or probably 10,000 or 100,000, and it's going to implant. So you're giving it that amount of kinetic energy by the voltage it's going through. So it goes through a 10,000 volt difference, and it becomes a 10,000 electron volt kinetic energy. So you can see. And through